This is completely, I don't understand this whole thing. I mean, if all that you want to do is just come here and sit in the class and that's it, then I don't understand. I mean, why am I even teaching? You should say at least something, you guys. This is whatever. I'm really fed up about teaching this in this mode without any answer. Anyway, so we are going to do today single source shortest path problem. Okay, what is the single source shortest path problem? Okay, let's see. So we have seen that the distance between two vertices, u and v, that is usually counted as the number of edges in the path between u and v, shortest length path, and that is defined to be the distance between the two vertices u and v in a graph. So this is the distance in an unweighted graph, right? And once I have to find out what is the distance between these two, how can we come up with an algorithm for that? So a simple one is to the simple okay, whatever. So yeah, good. So so how do you compute shortest path between u and v? So we have seen
Sir,
that, yeah.
Sir, actually, I'm sorry. It took me some time to unmute myself. That's why I was not able to tell you. Actually, we JRFs had decided a time, not exactly a time, a date, 28th of May, but I think 27th is fine with everybody. I
I
don't
can
know
understand
when.
that you took some time to unmute, but what about the rest of the JRFs? Are there any other JRF in the class? Is there any other JRF in this class at this point?
Yes, yes, sir.
Sorry?
Yes,
Yeah,
sir,
Mayank Deoda, you're there, right?
yes, sir.
So you
Sir,
also did not unmute and say that you had discussed our time.
yes, sir, we had discussed and we didn't have any problem with this date, so that's why I didn't say.
Okay, fine. I mean, whatever. So 27th, that's what it is. I mean, any other JRF? There's only two JRF in this whole batch right now.
Sir, I'm JRF.
Aditya, right?
Yes, sir.
What about you?
Sir, due to connection issues, I joined late.
Okay. Any other JRF who was there at the time in the beginning? No other JRF? Let me launch a poll. Let's see. Because I find it to be very, I mean, disrespectful that when I'm saying something, when I'm asking something, none of you even answer me, yes or no. And this is really, I mean, okay, good. So anyway, so 27th is this class, and as I understand it, from repeated questioning and all, none of you have any doubts whatsoever of whatever has been done in the class so far, and so I am basically continuing with this thing. Okay. Yeah. So we were computing the shortest distance between two vertices u and v. and the distance is the number of paths from U and number of edges from U and V. Now, how do you compute the shortest distance between two vertices U and V? So one of the simple things to do is, we have discussed this one in last class or last to last class, that you can use BFS to do this shortest distance. And this is what has been what we have discussed, that this is will give a linear time algorithm for finding the shortest distance between two vertices. But there can be more complicated graphs. Namely, there can be weighted graphs. So what is a weighted graph? So every edge is assigned a number, integer number. Sorry, not integer, a real number. And in general, this number can mean lots of different things. But for this class, we will assume that these numbers indicate the, say, the amount of time taken to traverse that particular edge. So the shortest distance will be defined as, so given a path, the distance of that path is the sum of the weights of the edges, weights on the edges in that path. So that is the distance in a path. And among all the paths in the graph, the shortest path will give you the shortest distance. The shortest distance between U and V is the length of the shortest path from U to V. Right? Now, how do you compute this? Now, this is a problem that I can ask you guys to think about it, that if I give you a weighted graph and I ask you to do a BFS or something like that, that need not give you the shortest path between two vertices. Because it might very well be that all the vertices that the BFS is finding out is length infinity, whereas there is possibly a much more convoluted path between that vertex and V, U and V, whose lengths are much smaller. So how do you find such paths in that weighted graph? Now, say for example, here there is a graph and there are the edge weights that have been presented here. And what we want to compute is what is the path from G to A. So how do you compute that? Or what is the shortest path? So of course, there is a path like this, say G to E, E to C, C to B, and B to A. So this path has length how much? So 9 plus 5 plus 8 is 22 plus 7, 29, right? The length of this path is 29. And is there any other path? Is there any shortest path? So of course, I could have gone from E to B instead of going from E to C to B, and that would have given me a shorter path, G to E to B to A, and that would give me a 23. And the question is that, is this the shortest path that exists? And if you look at it carefully, you realize that there is a path of length 22 in this graph. And that is G to F to D to A. Now, already in this picture, you can see that actually finding out the shortest path between 2 points is not the easiest thing. It's not immediately obvious. And so we will be spending time in this class and the next class, and this everything will be there very much as a part of MidSem, that how to design algorithms to find out the shortest path between two vertices. Now, this problem of finding shortest path in weighted graphs is of an extremely important concept. I mean, not only is it used in the standard, standard softwares like Google Earth and all those Google Maps to find out the shortest path between two points and so on. It is also used for lots and lots of other things, where the edge weights does not necessarily represent the time to traverse, but might represent something else and so on. So finding out the shortest path between two vertices is a one of the most important concepts or most important problems in this field of graph theory. And this is what we will try to solve. Any questions? No, thanks. So let's continue. So, okay. So if I want to find out the shortest path, now, okay, can the weights be negative? The actual answer is that yes, it can be. There are incidents where when you consider a particular problem and you model it as a graph theory problem, you might incur negative costs. Okay, negative costs can represent various kind of things, and we will actually see the concept of negative path sometime later on in this course when we will talk about flow, and so it will come up. But when there is a negative path, there are certain things that you have to keep in mind. So for example, here I have made this age from D to E to D minus 5. Okay, makes complete sense. Okay, so this graph consists of a path from G to A, and the shortest path now will become, actually, if you think of it very carefully, it will become G to E to D to A, where the cost will be actually 9. So there was the length of 29, 23, 22, and then there is the path length 9. So 9 length 9 path will be there from G to A. Now, we call a cycle, a directed cycle, as a negative cycle, is the sum of the weights on that cycle adds up to some negative number. If it is the case, say for example here, I have converted this age from G to E into minus 9. So here, there is a path, there is a cycle from G to E to C to G, this path has total weight minus 2, minus 9 plus 5 plus 2, it's minus 2. So now, if I ask, what is the shortest path between G to A? Can somebody say what will it be?
As low as possible, because we can revolve around cycle.
Yeah, we can revolve around this cycle, right? So we can have a minus 2 path, and we can basically keep on moving around the cycle for any amount of time, and then I can at some point decide to go to A. So it depends on how
So
long.
can you explain?
Sorry.
So can you repeat it again?
Okay. So this path, are you? Did you understand that this cycle has negative weight?
Yes, minus 2.
Yes. So what happens if my path is of this form? Okay, G to E to C to G to E to C to G, E C G, E C G, E C G, E C G, E
Okay.
A, E A.
So it will become lesser.
Every time I make a loop around this cycle, my path length will go down by 2. Right. So and then depends on how much time I want to spend, I can keep on going on this path for ages and ages and ages, and then at some point I'll go to A. And so the path will become, therefore.
So I can reach
Yeah.
from G to A.
Yeah.
I can reach by like minus time also.
Yes, that's the thing. We will be reaching in minus time. We can reach in minus infinity. So the distance between
Minus,
G to A becomes minus infinity. Okay. So this is a kind of something that we have to be a bit careful. Okay. Just like in the case of say topological sort, we told that okay, if the graph has a directed cycle, then the whole concept of topological sort does not make any sense. Similarly here, if a graph has a negative cycle, then the whole concept of shortest path between two points doesn't make any sense. So it is important that we know that okay, there is no negative cycles. There can be negative edges, but we have to ensure that there is no negative cycles. And so these are the usual assumptions that we take. The first assumption is, which is universal, that there is no negative cycle. And another slightly more complicated one, or point more, is that you will see is why we will be assuming this particular fact, that we will be sometimes be using the fact that there is no negative weights also. Negative weights are harder to handle. Okay, negative weights are much more harder to handle. Now, maybe let me pull it here. What happens here? Say, what happens? Say, I have this kind of path, and why did I say that there is a negative weights are harder to handle? So this is the graph which has one negative edge. What happens if I increase the edge weights of every vertices by 6? Every edge weight becomes whatever that edge weight is plus 6. Then all the edges have positive weight. Then what's the problem? Then that should be done, right? Then I could have solved the graph algorithm in on the algorithm that works for positive weights, and that would take able to solve the shortest path between G to A in this graph also. Do you see any problem in that? No. Yeah. Someone? Swagata Sasmal, are you there?
Yes, sir.
Yeah, do you have any idea what happens if I have this graph and I increase all the edge weights by 6? So this becomes 11, this edge weight becomes 13, this becomes 15, this becomes 1, this becomes 12, and so on and so forth. So now I will get a graph on positive edges. And if I solve the problem in that new positive graph, I will get a shortest path between G to A. Right?
Yes.
And that path will be the shortest path in the original path of graph also. Correct?
Hello, sir.
Yeah.
Sir, in
Yes.
this particular graph, there will not be any problem, but in a general graph, let's say the shortest path has like 4 edges, and there is another path which is greater than it, but it has 3 edges. Then if we increase every path with 6, then the shortest path will get increased by
good, very good.
24.
You have understood this. Let the other people also think of it here. You've got good that you've got it. Yeah.
Yes, sir. Hello.
Yeah. Hello.
Hello.
Yeah. Tell me.
Yes, sir. If the source to destination path have, if the source and destination path have more edges, then there will be problem.
What do you mean source to destination path of more edges?
I mean to say, if there is a shortest path, if there are several paths, and suppose there are less number of links in the path, but still it could be it could have more weight.
Okay, I think also you are kind of understanding this whole thing, and maybe you are unable to put it properly in the words, but.
If there are suppose 4 from G
Okay,
to
good.
A.
I understand what you are saying. Yeah, okay. I mean, try to say it in a bit more formal way. Okay, think about it yourself. Let me go over some other people. Mahesh Reddy, are you there?
Yes, sir, I'm here.
You have any idea about this thing?
Like the thing which you told that, basically adding 6 to every edge, and then you said that should be the same path. I was just not convinced with it, sir. So I was thinking about that.
Yeah. So, I mean, why are you not convinced? That's the thing. You are right. If you're not convinced, that's good that you are thinking you are in the right direction. You should not be convinced. I mean, that statement is wrong.
Yeah,
But you
because
have to tell me why.
Because because we took this example of -2, right? When the previous example where this
Right, good.
cycle
Very
EPG got -2, when we added if we use the same logic and add things, we'll basically, so that infinite path won't exist.
Yeah, that's true.
Yeah.
Very
So
good.
yeah. So, but the same way, if we actually do it in the other way, like as you
Oh.
said, if this
Yeah.
should be the path after I improve 666, then
Right.
this should be the same path when I reduce, but that's not the case.
Right.
Yeah. So that was why I was not convinced with it. So I was thinking about.
But I mean, where is the logic going wrong? I mean, you understand, you are saying that, okay, if that was the case, then the infinite pipe will disappear, right? But why is it disappearing? I mean, what is it wrong? I mean, we are making some mistake, right?
Yes, sir.
Gary, are you there?
Hello.
Yeah, are you there? Yeah.
Hello.
Hello, are you there? Can you hear me? Okay. Gary Rene, you seem to be unmuted only. You have me muted only. Can you unmute?
Hello.
Yeah, hello. Yeah, Luna, you have some idea?
Sir, Avanish was already telling that it's like if we are adding the same number 6 to all the edges, then the path from one vertex to another vertex will not always be of the same number, same
So what
length.
will it be? What will it be? Can you just say? So say I have this graph G, right? I have done a G prime, which is nothing but G plus 6, meaning every vertex has got, every edge has been added 6 edges, right? Now I have a path
Yes.
here. Okay, so the weight of the path in this here is G, this one. What is the weight of the path in G prime? What will it be?
It will be 6 into length of the
Will be 6
Yes, sir.
into
Earlier
the
path
length
plus
of
6
the
into-
path plus the weight of the path, right? And
Yes.
because length of all paths are not same, there are some paths of smaller length, some paths of bigger length. So different edges, different quantity will be added to different paths. Right? Different quantity. If the path is of a small length, less amount will be added. If a path is of a big length, big amount of things will be added. So it is very much, so it will give an unfair advantages to paths of smaller lengths. So it's very well possible that if the weight of P1 is less than in G, is less than weight of P2 in G, but when I look at the weight prime of P1 in G prime, this changes. Right? The weight might have changed. Hello? Hello, can you hear me? Yeah.
Yeah, yes, sir. Yes.
Yes, sir.
Yeah. So because these two paths, P1 and P2, P1 might have more length, but I mean more number of edges, but less distance, and P2 might have less number of edges, but more distance, and that's why this was the case. But when I'm adding 6 to them, this flips. So it is important to note here that many of you have understood it correctly, and if you have not understood it, think about it a bit more. That just adding edges, some constant amount to all the edges to make them all positive is not going to make the graph into a positive graph so that you can solve the problem in that. So instead, we have to deal with negative edges in some other way, and that we will come to it a bit later. So for now, I will be assuming both of these things to start with in today's lecture. In on Thursday's lecture, we will see how to get rid of the assumption of negative weights. Okay, good. So let us first assume that there is no negative cycle and no negative weights. And the idea is to find the shortest path between two vertices. Okay, shortest path between U to P.
And one question.
Yeah.
When we are saying shortest path between two different vertices, that path should have unique vertices or the same vertex it can travel multiple times.
I mean, it can travel multiple times, but yeah, if it is positive edge weights, having same vertex multiple times is only making your life harder, right?
Yeah, but I read somewhere path means the vertex should.
Yes. So I mean, if you
walk
want to,
means
right. No, okay. So you want to say something about in the case of something for the negative cycles, right?
yes.
Yeah, for the negative cycles, there are such issues. Okay, so there is algorithms that can handle such issues also. Like how can you ensure that no edge vertex is added, used more than once, and so on. But those are much more complicated, and I don't even think that we will be able to talk about that even. Okay, there are algorithms, but they're complicated. But the main idea is that if I have a path like this, okay, U to V, and if this path is positive, then this path is just making my life worse, right? So in a negative, if I have a positive graph and basically a positive cycle over here, then it makes no sense to use the same vertex multiple times. So you can always assume that the same vertex is used only once. Yeah, for negative cycles, that's a bit more trickier. Okay. Now, okay, so I will be using these notations that W of any two vertex edges between two vertices is the weight of the that edge. Now, here is a very simple algorithm. Okay. So, say I want to go from a particular vertex. Say maybe I'll go and draw something more. I have a graph here. Right? Say I have a graph. And then there are a lot of other things up there. Okay, so there's U to V. Now, if I am looking at paths from U to V, one thing that I know is that a path must leave the U at somewhere, right? So it must go through either this vertex or this vertex or this vertex. These are the only three. It has to go through its neighbors. Now, and once I leave this U, right? And once I leave this V, and once whichever way I go, then I am not going to come back. Now imagine this thing, okay? That you are say you are taking a flight from say Calcutta to New York. Okay. Now you want to find out what is the cheapest way you can go from Calcutta to New York. So instead of trying to really put in a lot of effort about all possible paths and all those kind of stuff, what you find out that, okay, if I leave from Calcutta, I can take a flight to Bombay, or I can take a flight to Delhi, or I can take a flight to Bangalore, or I can take a flight to say Dubai. And from there, maybe there is some other path. So maybe from Bombay, the cheapest flight is from Bombay to Dubai to London to Toronto to New York or something, much more complicated. But instead of you doing all the hard work, what you tell is that you send your friends. You ask your friend in Bombay, what is the cheapest path, cheapest flight cost from Bombay to New York. So your friend says some number, say 1,000, say $1,000. Oh, okay. You ask your friend in Dubai, what is the cheapest flight cost from Dubai to New York? You ask your flight from, so maybe if I can just write it down, okay? So say this is where I am. So right now I want to go from Calcutta, and you have this possibility of you can either go through Mumbai, or you can go through Delhi, or you can go through Dubai, or you can go through Bangalore. Okay. Now your friends have managed to find out that from Mumbai to New York, the cheapest cost is say $1,000. From Delhi to New York, the cheapest cost is say $1,200. So Dubai to New York, the cheapest cost is say $800. Note that it might be that Mumbai's cheapest thing might involve going through Dubai. That we don't know. From Bangalore, say the cheapest price is say $1,400. Right? Now from Calcutta, you know that, oh, for Calcutta, if I want to go to Mumbai, that will cost me $200. From Calcutta to Delhi, that will cost me $100. From Calcutta to Dubai, that will cost me $300. From Calcutta to Bangalore, it will cost me $200. Now see, note that these things you have not even done. So these things, if I draw this one, this whole information has been done by your friend. Okay. Now what you do? How will you do it? How will you find out the shortest path from Calcutta to New York? Can somebody say what is the shortest path from Calcutta to New York? How can you find out, or cheapest path? Joan Maitro, are you there?
Yes, I can add them and then find the minimum.
You can add them. So from Calcutta, you can say that, okay, if I go through Mumbai, then the total cost will be 1,000 plus 200 is 1,200. Ah, very good. Through Mumbai is 1,200. Through Delhi is 1,200 plus 100 is 1,300. Very good. Through Dubai is 800 plus 300, 1,100 or something like that. And you can take the minimum of them. Okay. Now, this is kind of a recursive approach that you don't do the job yourself completely. You ask your friends to do the job. Now, why will your friends be able to do the job? Why will they be able to do a job anything better than what you can do? Because when they compute this cost from Mumbai to New York, they will not consider going through Calcutta. So for them, the graph in which they will search have one vertex less. Okay. So from here, if I have to go from U to V, I can ask, okay, now see, here you are, you go and find out the shortest path from all the blue vertices to V. And now, how will they do it? So so for example, say this vertex, the W, they will find out the shortest path between W to V in this graph, G minus U. This will also do the same thing. This will also do the same thing. And U, all it will do is that after it has done all of it, it will check out all its neighbors and find out the minimum. Right? So this is a very simple way to do. The shortest path from U to V is the look at all the W's, look at the distance from D to W, and this D meaning just the one edge, distance of an edge. Okay. Oh, sorry. I'm okay. So this is done in the opposite direction. So DWI is the distance from U to W1, WI. So look at all the edges, distance from U to WI, and the edge weight between WI to P. Right? And that would give us the algorithm. Correct? So say for example here, okay, this is the opposite. I didn't do it in U to P. So I have this G to A. So what do? I will, for every vertex W that are in the incoming neighborhood or in degree or in neighborhood of V, what do? I calculate the shortest path between U and W in the graph G minus V. I forget the last vertex. Okay. What is the shortest path from U to W in G minus V? And once you go from U to W, then I'll add the price of W to V, and that would be the shortest path between U to V going through W. And if I take it minimum over all possible W's in the neighborhood of V, I would have done it. I would have got it. Is this algorithm clear?
Yes, sir.
Sir, how is it working?
How is it working? I mean, what do you mean by that? So I claim that this one, okay, what is this one?
This one means the initial vertex that we are not considering.
Not the initial. So here, the way it is written, I have explained them different way. The last vertex you are not considering. Okay.
The last vertex. That means it is the last vertex means this is the initial vertex, right?
U to V.
U to V.
Yeah. So I mean, just like I kind of described this whole thing in terms of the going to.
Then we should subtract U, right?
Yeah,
G
I
minus
understand.
U.
So when I explained you, I had explained it in terms of removing the. Okay. Yeah, I made a mistake over there. So I explained you by removing all the vertices going out of U. But note that similarly you can do the opposite direction also. Right? Similarly, what you can do is that you can say that okay, it is not just U to V. I can say that okay, what are the paths from which you are entering? So this is the places we can enter. Enter V, I have to enter from this vertex or this vertex, W or X. So what I can do is that this is just the opposite, just the same thing. That I will ask W to compute the shortest path between U to W in this graph. Okay.
Okay. So
and I'll ask X to compute shortest path between U to X in this graph. And the shortest path between U to V passing through W, whatever that edge is that cost plus the cost of this edge. Right? What is the cost of here? This is the shortest path going from U to X and plus cost of it. Right? And the sum of these two will give you the shortest. Not short, minimum of these two. I mean, this is exactly the opposite of what I just explained. I explained it from U to V.
Sir, I So I have like from that V to X, if the weight is more, sir, can you just scroll down?
Yeah.
Yes.
Yeah.
Yes. So from B to X, if this weight is more than the composite weight of V to W to X, then how that can be calculated? How this algorithm is calculating that minimum?
Okay, it's the minimum of what? So say here, so W will report.
For example, V to X.
So W will report to me that. So W will report to me that okay, U to W the shortest path is 100. U to X says the shortest path is 90. Now W to V, the shortest path is say 10. I'm not shortest path. The length of the edge is 10.
10. Okay.
X to V, the length is 11. Then what is the shortest path? So W, right here, is going to report to me that okay, see the minimum path from U to W, not going through V. Forget V, but everything else is considered, is 100. So maybe there is a path like this, right? Maybe there is a path something like this, like I don't know, that's 100. right? And
Okay.
now there is also a path. What X is saying is a path like this that goes to X. That is 90.
90.
Okay. Now what does V do? Now V says that okay. Now if I have to come from W, so U to V, I have to enter through VW, or I have to enter through X, right? I have to enter through one of these two, right?
Yes.
So if I have to enter through W, so I have to first of all find out the shortest path between U to W, and that length is 100. And in that case, for me to come to V through W, the shortest path length is 100 plus 10, which is 110. Similarly, shortest
Sir?
path length from U to V through X is minimum can be a 90 plus 11, which is 101. Okay, so minimum of 110 and 101 is what.
Sir, here is the okay. So from X to V, if instead of 11, if it is 20, suppose.
Yes, it's 20. Okay, fine. Let me do
If it is 20, and from X to W, there is a weight called 1.
Yes, fine. Yeah. Now tell me
No,
which one will be chosen?
not that one. X to W. X to W.
Oh, okay, very good. X to W. This is 10 only, and this will be 1.
Yes, this is
Yeah.
yes.
Right. Good. So tell me, can it be?
So from here we have to calculate the calculating the minimum distance up to W will not sufficient. Will not be sufficient.
Why not? Why
because if from U to W, if we find out the value as 100, and from U to X we found out 90, then from
Can you find that one out? Is it possible?
Yes, sir.
As you have described, is it possible?
Which one?
What happened this one? U to X to W. What is the length of this path?
91.
And how is my 100 coming there?
Okay. Okay.
See, U to W is the shortest path that involves everything except V. That's it.
Okay. Yes, sir.
Okay, U to W contains the shortest path that contains everything except V. Okay. So it cannot be.
Yes, sir.
So I mean, basically, consider the shortest path. Okay. So forget all of this. Here is the graph. Here is the U. Here is the V. Here is the W. Okay. And somehow somebody says that here is X and here is Z and whatever, all of that, X, Y, Z. And somebody says that, okay, so the shortest path is this. Okay. Then what is the shortest path from W to V? If the shortest path is the orange line, what is the shortest path from W to V?
That portion, that color.
It has to be this portion. Why? Say, maybe there is another shortest path. No. This one is the shortest path. Okay, let's now calculate it. So let this be the edge weight is say E. Say this distance is D. So the shortest distance between E and V is E plus D. The distance between U and V is E plus D. That is something that is given to me. Is the shortest distance, right? Now, if there exists a path from W to V, which is a different distance, D prime. So if there exists W to V of distance d prime, which is strictly less than d, then what is the distance between u to w to v via this path? What is this? This is E plus D prime, which is strictly less than E plus D. But this is not possible because here you have kind of claimed that E plus D is the shortest path. Right? So this must be the shortest distance. I mean, if you give me a shortest distance from U to V and look at the neighbor of U, then the shortest distance between that W and V has to be the shortest distance between that vertex and V. Okay, is this clear?
Yes, sir.
Okay. Yeah, it's actually, I mean, it's a good that you're asking this question because these are actually not obvious. And I am kind of skipping over a lot of this kind of formal proofs. I am trying to give you the intuition over here. Once again, I am asking you guys to go and read the books at least once to see the formal correctness of this algorithm. I mean, whatever has been just now described is the formal correctness of the algorithm. And basically, what is, I mean, the theorem will say that the shortest path from U to W, U to V, if it goes through W, okay, then that path will be the shortest path from W to V also. Okay, and once you have that, then if you apply this particular algorithm, you will be done. Now, okay, good, very good. So how is, but what is the running time of this algorithm? Can somebody tell me? Kaushali, are you there?
Yes, sir.
Yeah, what will be the running time of this algorithm? Can you tell me?
Running time.
You understood the algorithm, right?
Yes, yes, but I need to think of the running time.
Rupsha, are you there? Yeah, you have any idea?
Sir, like let me think for some time, then I can say.
Okay. Hornolipa, can you help me?
Hello.
Yeah.
Yeah, sir. Actually, I'm also thinking. Actually, I mean, I haven't yet figured it out.
Okay. I mean, you don't have to figure it out. Can you tell me how to approach?
Like there is n vertex, so
Yeah.
maybe. Can you see? Can you like? Can you see the graph? Can you see the graph?
This one or maybe this one? Oh, sorry.
This one. Okay.
Okay, think about it. I'll just be back in a second. All of you think. What will be the running time of the algorithm? This is the algorithm.
Order of n square.
Yeah, guys. So did you figure out how to calculate the?
Sir, can we like add? Can we have an adjacency list? Like in the adjacency list, we will like order the vertex based on their weight. Like less weight, then we can put it up, and like doing this, we can say like maybe order of like n square. N is the number of vertex.
How will you do this calculation? D of U W G minus V.
Like in the adjacency list first. Oh, okay. Someone is telling something.
Sir,
Yeah.
like can we say it in terms of recurrence relation?
Yeah, you can.
So T of n equal to like if we remove the last destination vertex, then T of n minus 1 times in degree of that vertex.
Very good. Very good.
Plus.
Yeah. So this is something that you should
again,
remember.
in degree. Yeah.
That always, whenever there is a recursive algorithm, an algorithm that calling itself, then the only way to solve the running time is by solving a recursive line equation. Okay. See, it's a recursive, so you have to be very careful over here. Okay. It is not like in one loop or something happening. It's a recursive call. So first of all, let's say T of n is the time taken to solve this algorithm on a n vertices graph. In that case, this one is an n minus 1 vertex graph. Solving it the same recursive language. So this is T of n minus 1. Of course, you can add them up. And how many times you have to add them up? You have to add them up the degree or in degree of the vertex. And you have to take the minimum over all of them. That also takes that will also take in degree. Since the in degree is at most n minus 1, so we can, okay, so we can write it something like this. T of n equals to or less than or equal to, rather I would have said, n minus 1 times T of n minus 1. And if you solve it like this, you will realize it that T of n is n minus 1 factor. It is not a polynomial time algorithm. It is an horribly bad algorithm. Okay? The reason is that you are evaluating a lot of things multiple times. Say, for example, here, say here, right? So think of this graph, okay? The person who is computing the shortest distance from Mumbai to New York is possibly actually also solving the shortest distance from Dubai to New York. So the Dubai to New York possibly is being solved by Dubai to New York once, is being solved by Mumbai to New York, is being solved by Delhi to New York, is being solved by Bangalore to New York. So the same computation is being done by 4 different people independently. So it's a lot of wastage that's happening. Okay, or maybe the shortest from Mumbai to New York is actually going through Mumbai to Delhi and Delhi to New York. And that also, again, Delhi to New York is being calculated multiple times, right? It's true that all these computations are being done in one vertex less, but there are lots of the same thing, the same pair of vertexes is being studied multiple times. Okay. So this is exactly what happens when you are trying to, when you do a recursive kind of a call like this, and multiple times, it's very well possible that the same subproblem is being computed again and again. So that is why this particular algorithm is a very inefficient algorithm. It's a correct algorithm, but it's a very inefficient algorithm. But is the computation of this one clear? Did you guys follow? Ruksha, did you follow this one?
Yes, sir. Yes, sir. I follow this one, but how the like graph is saved? Like
How the
we
graph?
have to save it.
Yes, the graph is saved in an adjacency list. I completely understand that. But that is not, that doesn't matter at all. Whether it is saved in an adjacency list or adjacency matrix or whatever, the finding the minimum will take order n steps. Okay. And it is all that is because of this call, recursive call, that is actually doing all this, all the damage to the.
Sir, actually, we can come up with a better estimate by using AMGM inequality for degrees, in degrees.
Yeah, so you can do it with a little bit of a in degree kind of stuff, but this is the worst setting. So that will become, yeah, you are right. You can do a little bit better, but it will still be exponential. Let me put it this way. Okay, it will still be exponential. You can go and do the calculation. Yeah, it will still be exponential. Okay, I mean, for a particular graph, when the graph has n vertices and m edges, you can do a little bit of optimization because this n-1 is not n-1; it is the in degree. I mean, this n-1 is just a kind of the worst case kind of setting. Okay, good. Now, how do we do that? Can we do better? And the main idea is to reuse the computations. And this is something that many of you might have already seen it in some sense, in your previous courses or something like that. And the main idea is that, okay, here, I want to compute the graph between the shortest path between G to A. Okay, that's the goal. I am forgetting A. Okay, I know that from G at this point, I have this whole graph. A is too far away from me for me. I am not even going to think of trying to solve the shortest path between G to A. Instead, what I will do is that I will find out all the shortest path between G to all the vertices. It's a single source shortest path. Okay, forget it. If somebody says that, okay, see, I don't know what is the shortest path between the Calcutta and New York, I will find out the shortest path from Calcutta to all other cities in the world. It doesn't sound to be a very efficient algorithm, but surprisingly it works. Now, here is it. Okay. So, one thing that we can do is that we look at all this G. Okay, so G is there. So at this point, the main idea is that I am at G. Okay. Now I can go only to two places from here, right? E and F. Is it possible that what is the shortest distance from E to G, or what is currently the shortest distance from E to G? It is by going from G to E. It is going via this edge of Hn 9. What is the shortest for us from G to F? Right? It is F. It is 11. Okay. But I know that, see, because I am dealing with a positive edge-to-edge graph, here I have to leave G in some way, right? So if I leave G and I go to if I go to G to E, I will incur a cost of 9. Is there any other way I can go from G to E that will incur cost of less than 9?
No, sir.
No. Why not?
Sir, because only two paths are available, one going through E directly and one going through F.
Yes.
But the path through F is already greater than the path that we are getting through
the path through F, just even going through F is costlier than going through E, right? And because there is no negative cycles or negative edges, So this cost, if I go to E via F, my path cost can only go up, cannot go down. So this is where I am using crucially the fact that all the edges are of positive weight. So at that time, I know that therefore, if I take the minimum edge going out of G, which is in this case E, then I know that E, the shortest way of reaching E is via this path. Okay, good. So this is one step. So the idea is that this red vertices will always indicate the shortest path, right? Shortest path by which I can reach E. So the vertices, set of vertices from which we know the shortest path. So for E, I know the shortest path from G to E. Now, which is the next one? At this time, via E, I can go through C, and the cost will be 9 plus 1, 10. I can go to B, cost will be 9 plus 7, which is 16. I can go to D, which will be 9 plus 5, which will be 14. I can go through F. Okay, I can go through F some other ways also possibly, but I can go through F directly, and that is 11. And at this point, I should say that, okay, see, among all the rest of the places, again, at this point, if you look at all of them, the C is the minimum that is there, right? So if I go to C, the cost is 9 plus 1, 10. And that is more than all the other paths that I can go from the red edges, red vertices. And so there cannot be among the set of vertices. So note that at this point, I've not even looked at A. I don't even know there is a path from A to C or not. There might be a path from A to C. I don't even know that. But I know that since I have to go to C, I have to go through F, or I have to go through D via E, or I have to go through B via E, or I have to go through C via E. I will, and all of them are costlier than going through E to C. All the paths will cost more than E to C. And therefore, I know the cost to C has to be the minimum. This is the minimum cost. So this is a very crucial thing that we are doing. Now, maybe I can try to explain you in another language. Maybe that would be helpful another way. Okay. Say I am here. I know that, okay, here I am, and here are all of these places. Okay. And I know that the best way of reaching all the vertices. So among this set of vertices, there are the blue ones, okay, and then there are the red ones. The red ones. Okay, so at this point, think of it this way, okay? The blue ones, so this is G, this is say U. I know from U, the cost of going here is say 10, the minimum path. The minimum path to going here is say 11. The minimum path to going here is say 5. The minimum path to going here is 7. Minimum path to going here is say 9. And now there are the other costs that are there, okay? So there are this cost of, oh, and then this one, this 60. And now the idea is that, okay, here there is a path 5, then 3, 2, 5, 4, 6, 7, 3, 9, 8, 3, 4, 5, 9. So something like that. Okay. So there are all these paths. The blue ones are the ones in which I already know the shortest path from U. Okay. These are the things that I know that, okay, if I have to go through let's say U, so V, W, A, B, C, D, E, F, G, H, I. So if I have to go from U to C, I know the shortest path is this. If I want to go through U to A, I know shortest path is this. If I want to go through U to W, I know the shortest path is this. Okay. Now at this point, I find out that, okay, think of it this way, that these are all your close friends. Okay. So all these people, they have found out the shortest path from you. Okay. Now this one, the other ones, they don't even know what is the shortest path from you. So what can they do? What they can do is that they can say that, let's look at E. Okay. E can say that, see, I can come to, maybe I can add some more. Maybe there is a path from here to here of path 9. I can come to E from W. Then the cost will be to reach W. The shortest path is 11. So to reach E through W, the shortest path will be 9 plus 11, 20. Excellent. I can come here of 16 and I can go here for 5. So shortest path of going to E through this D is 16 plus 5 is 21. So that means at this point, if I am to reach E, the best that I have is 21. Okay, maybe I'll add. Now similarly for F, I can do the same thing. Okay, the shortest path, I can come from F from D, which is 16. It will be A6. To come from, for G will be 16 plus 8, 21. And so on and so forth, right? From 8, it would be 8 plus 7, 15. So this will be 9 plus 4. Okay, so 9 plus 4 is 11, 13. At this point, the idea is that I know that to reach E, the shortest path is 21. Now, should I take this path? Should I fix this path? Should I say that, oh, therefore 21, and so let me take this path? Is this the right thing to do? Can I, at this point, with whatever knowledge I have, say that the shortest path from U to E is 21? No, not 21, sorry. I should have told it 20, right? Shortest path is 20 from here to here, right? Yeah. Can I say that? It's 20, not 21, 20. What do you think? Manish, are you there?
Yes, sir.
Yeah. Do you think the shortest path from U to the E is 20?
That we can't say.
That we can't say. Why can't we say? Yeah, the reason we can't say is that it might be that I have only looked at the blue vertices and one step before, right? It might be that there is a blue vertex, I can go here, which is not a blue vertex, and go here, and that might be shorter. And if you think of it, it might be the case. So if in case if this is a age 1, then this becomes 19. Right? That we cannot say. But among all the vertices that have not been touched, note that this vertex 13 has the minimum. It's 13, 15, 21, 18, 20. This is the minimum. Okay. So that means to reach, I can reach U to be in 13 length. Now I have to, so consider, let me draw a boundary wall. Okay, think of it, this is a boundary wall. Yeah, that might be better. So this boundary wall is something that I know. Okay. Now, if I have to go anywhere outside the boundary wall, I have to cross the boundary. And if I cross the boundary, I know that to reach to this thing, cost that it takes me is 13. To reach any other place, the cost that it takes is more than 13. So at this point, I can say that this vertex must be, the minimum distance is 13. Why? Because if there is another path that crosses the boundary wall and does lots of things and then comes back, but that means to cross this boundary wall itself, this cost is more than 30. How can the cost go down? Right? So this one, so at any point of time, I have the boundary wall. And if I look at all the vertices that are just beyond the boundary wall, the vertex with the minimum distance on that will be certainly be a vertex that has that I can add to my boundary wall and say that that is the minimum distance. Did it make sense? Manish, did you follow?
Sir, I didn't get why 13 is minimum.
So can you explain it to
what if
that
the vertex
graph?
So what if the vertex has 2 in degrees instead of 1?
Yeah, a vertex can have 2 in degrees. That's fine. Okay, maybe let me just think of. Okay, let me take care of this. So this is my U. Okay, this is the set of vertices for which I know my distance, shortest distance. Okay, this is my boundary wall. Okay, there can be other edges in this graph that I am not interested in. Okay, so there might be other edges. There can be lots of other edges. Okay, I'm not interested. But this, but the green vertices are the one for which I know the shortest path from you. Okay, is that fine? So there's A, B, C, and D. These are the vertices from which we know. Okay. Now then there are some vertices which are blue in color, and they are the ones that are outside the boundaries. Okay. Now there are some vertices which are even further away. So they are the red colors. Now what all things do I know? I know that from here there are some edges. Maybe there are some edges from all of them. Okay. They can be just like this. Okay. Something like that. So note that it is very important to remember that this is the boundary wall is here. Okay. And outside the boundary wall, the blue vertices are the ones that are just one step away. If I take one more step, I will go to the blue vertices. Okay. Now, for each of these vertices, I compute the shortest distance from the U. So from U, I know that say A, what is the distance? Minimum distance is say 5. Minimum distance here is 6. Minimum distance is say 8. Minimum distance is 9. Okay. And for all of them, all the blue ones, what is the distance? Now, what is the minimum distance of U? It is, I can go to A and then take this path, right? Or I can go to B and then take this path, right? Or I can, of course, go through a much more convoluted. I can take A, B, then go this path, and then maybe this path, something like that. So there can be a path like this also. Or, so say after all of that thing, I compute that, okay, if I am at this point and if I am using, so which is the next step for which I can say that it is the minimum distance? I know that this is the boundary walls, okay? So all of them I know the very well. So if I have to step out, so think of yourself, okay? This is your house, okay? This is your house and this is the boundary wall around your house, okay? Now that means at this point, you know everything inside your house very well. You want to step out. You want to go to the market out here. Can you go to the market immediately? No, correct? You have to cross the boundary wall and go to one of your neighboring places. And then go to the further ones, right? The first step that you will do will be going to the neighboring places. Now, at this time, I can say that, okay, if I have to go to the neighboring place here, then the cost of reaching here will be, say, 5 plus, say, 5, which is 10, or 6 plus 3, which is 9, or 6 plus 2, which is 8, or 8 plus 1, 9, so 6 plus 1, 7, or 9 plus 2, 1, some kind of stuff like that. 3. So at this point, for each of this point, okay, so I have these 4 points, X, Y, Z, W, and R. Okay, these are the places that I can go just one step beyond my boundary. What is the cost of going through X? What is the minimum cost that I can incur for going through X? Now it says, see, if I am at the boundary, if I just step out and first place that I step out is X, then what will be the cost be? Then I have to enter through this route or through this route. In that case, my cost will be, in that case, okay, so I mean write it in red. In that case, the cost will be minimum of these two. So maybe it is 9. So in 9 step, if I costing 9, I can go through U to X. That doesn't mean that this is the shortest path from U to X. What is this? If I step out of my boundary wall and the first place I land is Y, then what is the shortest path? Okay, you can be, okay, 6 plus 2, okay, 8. There's only one option. Oh no, there is a 1. There's 8 plus, there is an 8 plus 1, which is 9. Or I can go through here and 2, which is 6, or 8. So 8 and 1 is 9. Okay. Similarly for Z, if I am to come out and first thing that I step on is Z, then the cost will be 11. If I first thing I step out is W, then the cost will be, okay, I cannot step out and step on W. W is not the first step, so sorry. And what happens if I step out and step into R? What is the minimum cost? It would be 8 plus 1 is 9, right? It would be either 8 plus 1, which is 9, or 9 plus 2, which is 11, or it can be 6 plus 1, which is 7. So at this point, I can say that, okay, if, consider this one, I am in my house, I know all the places inside my boundary. Now, if I want to cross my boundary wall, I will step out somewhere. Which is the place I can step out? If I first step out at X, then I will incur cost of 9. If I step out at y, I will incur cost of 7. If I step out to z, I will incur 11. And if I step out to r, then I incur 7. At this time, I can say that therefore, see, since out of this 4, 7 is the minimum, I say that, okay, I will step out to this place, R. Why? And okay, I will step out. How much will I incur? I will incur 7 cost. Now, is it possible that there is another path from U that costs more than 7? So that is U to R that costs more than 7. Sorry?
Less than 7.
Less than or equal to 7. Or so less than 7. Yeah. Is it possible that something can be there less than 7? Hmm?
No.
Why not?
No.
Why not? Why not?
Because the neighboring places, whichever I go, the neighboring places has 9, 8, 11, and 7.
Exactly,
weight.
Because
so we have to cross them.
Exactly. Anywhere I go, I have to step out of the boundary wall somewhere, right? And as soon as I step out of the boundary wall, either I reach to R or I go to somewhere where already I incur a cost more than 7. Right? So it is not possible that R has, there is another path of length less than or equal to 7. So at this point, I can say that, okay, now I will try to update my boundary. Okay, I can say that now I know that this R, this is not only is it my thing, I will update my boundary wall and I say that, see, the boundary wall is now this, because I know that I can go to R and R has cost, must be costing 7, and that is the best thing. And what is the path that I can take? The path that I can take is from A to B to 7. It comes from here. Is this clear? Is this clear?
Yes.
Now
Yes,
there is no need to
Mm-hmm.
inside the boundary, right?
Sorry.
There is no need to update distances from you to every vertex in the boundary wall, right? After adding the new vertex.
Yes, that I have to do, right? After I've added this one, after I added this R, all the inside the boundary wall, everything is known. Everything outside the boundary wall might change. Right? For example, W earlier there was no, it was not even close to my boundary. Now it has become close to my boundary.
Okay.
Right? So every time I update my boundary wall, I have to redefine my whole thing. My cost of weights outside my boundary wall. Right? But the main idea is that at any point of time, if I have the boundary wall and I look at all the things that are one step away from my boundary wall, look at the minimum cost of reaching those from one step from my compound, the minimum of those has to be the minimum distance. Shiva, is it clear?
Yes, sir.
Luna, you are saying something?
Yes, sir. I understood.
You understand, right? So this is a bit tricky, I must say. It's not, I mean, if you don't think of it algorithmically, it will take you some time to digest whatever has happened. Or why are you doing it? Okay. But if you think of it a bit in yourself, it will become clear. It is not too complicated. The goal is that we are not trying to find out the shortest path from U to V. We are finding shortest path from U to everything. And our goal is that at every step, I have to add one more vertex and say that, okay, see, for this vertex, I know the shortest distance from you. And what is the vertex? That vertex will be among the set of vertices that are just outside my boundary wall, or that can be reached from my boundary wall by just one step. Look at all the minimum costs there and take the minimum of them, and that would be the path. And if you do it this way, then you will see whatever I have been doing here. And I don't want to take too much time over here, but you can see that by doing such thing, you can able to do it. So maybe if I just write a pseudocode here. Okay, so this is the main
Hello,
idea. Okay, yeah, go ahead.
Sir, so same thing can you explain with this graph?
Yes, I'm doing that.
For example, E2C, if I reach as at
Okay,
10,
so let's
the
start with
minimum
this. Okay, at this point
10.
at G, okay, so certain things I will say and certain things I will not say. So let's start with G. Okay, at this point the distance of G from G is 0, and how do I reach G? Of course, I'm at G and therefore I get it. At this point, what is the minimum cost where I can go? Okay, I can go to E at cost 9. I can go to F at cost 11. Okay, minimum of these two is 9.
Yes.
Right. So that means the next thing that
Yes.
I add into my boundary is E. Okay, and there is a E is one thing that I've added to my boundary, and I have reached there with cost 9. And I also maintain, how do I reach it? I reach this from G. At this point, my boundary is this one. My compound is E and G. Okay. Let's try to update the prices or cost of paths from everywhere. What is the cost of going to C? I don't have any path from G. I have a path from E. Okay. E to G, I know the minimum cost is 9. So G to E, C, by going through E is 10. 9 plus 1, 10. Right? Similarly, G to B by going through E is 9 plus 7, 11. G to D is 9 plus 8, 17. And G to F is 11. 11, 17, 16, and 10. So the minimum is C. I take C into my boundary. At this point, let me again update it. Okay. Okay. Now one thing is to note that all that I have to update is all of these things that are going out of C. Everything else will remain same, right? So B earlier I could have reached from E, which is 9 plus 7 is 16. I can now go from
16.
C, which is 10. C's cost is 10. 10 plus 8 is 18. But 16 is minimum, so that will be 16. So 16, 11, and 17. Okay, so 11 is the minimum. The next one I go is this one.
F.
Now I do this one again. F to E. Okay, it doesn't matter. It's within the boundary. I already know. F to D is 50. Right? See, till now D was 17, but now, so this is also 17. F to D is also 17. 6 plus 11 is 17. But I can update it. 17 and 17 are same. So it is 17, this is 16, and that's it. 17 and 16. So which one should I take next? I should take B. B is less. Oh, so actually I made a mistake. So there's an error in this thing. I should not have done that. Okay, sorry. So I made a big mistake. So this should have not have been 7. This should have been 9 or something. Okay, this one should have been 9. If this was 9, then this would have been 18, and then that would have been fine. Just one second. Yeah. So sorry. And then I should have updated, and that time A would have been updated to 22, and this would have been updated to 16, and I would have come to. So sorry, there was a mistake in this execution on the calculation. But you understand what was going on here, right? Every time I I look at all the vertices that are one level away from my boundary, and I find out the shortest one among them, the one that I can reach with the minimum cost, and that is one I'm adding to my set of things for which I know my distance. Okay. So here is the pseudocode. So don't worry about the pseudocode. If you want to pseudocode, you can use the pseudocode later on also. It is nothing. At any point of time, I am updating all the distances to all the neighbors of the places, things that are done, and I'm taking the minimum of all of this. Okay, so don't, I mean, I will not go into the pseudocode at this point of time. What I want you guys to do is that I will stop here now. I want you to go back, think about this algorithm. This is called the Dijkstra's algorithm. You might have seen it earlier also. I want you to go and read it from the book and try some problems, some examples. Okay, and you try to digest it. And in the next class, we will start from here. We will go over the Dijkstra's algorithm once more, and then I will go over the pseudocode and the runtime of this algorithm. But your job will be to read the algorithm from the book once again, and possibly follow this notes that I will upload it, and convince yourself that the algorithm is correct. Correctness of the algorithm is what is most important in this case. Okay. So yeah. So any questions?
Hello, sir.
Sir.
Yeah.
Can you explain the date of submission of assignment thing? I mean, for 2 days. So we have another assignment which is.
Yes, you have another assignment that you have to submit in on
22
on the Monday.
22. Yeah. Can it be extended for 2 days?
For 2 days, okay, fine. Extend it for 2 days and submit it. I mean, why 2 days? Is there any particular reason for that?
Actually, it's all. I mean, it will be complete by then.
Huh?
It will be complete by then.
I mean, I'm a bit shocked, I would say. I mean, yes, fine. 2 days is something that I don't mind. Okay. But I mean, the submission is another 4 days from now. And you are already so accurate that I will not be able to solve it in 4 days, but I will be able to solve it in 6 days.
I mean, the solution is in my mind, but I need to type it and also the code for the last.
No, that's fine. I mean, like, usually I get such requests much late in the submission time. But it's okay. I mean,
Okay,
take
so
2 more days. Yeah, submit it by
26th.
Yeah, submit it by 26th.
Hello,
Yeah.
sir.
Yeah.
Can you say whether this interpretation is right for this algorithm or not? Like looking at contour lines and going through the normal distances from the contour lines.
Kind of right. You're kind of right. Yeah.
It's like
kind
discrete was a thing, right?
Yes, you're kind of right.
Okay.
Yeah, but in the discrete world, so you have to be a bit careful over this one, but it is kind of right. Yeah, somebody else wanted to ask something? Okay. So if nothing, let me stop here. I will upload the videos and everything today. And as I told you, go over the Dijkstra's algorithm in the book and try to at least convince yourself of the correctness of the algorithm. The book will, of course, have the full formal proof of it. But as I told you, I just wanted to give you a abstract, I mean, the high level picture of what is going on. We will go over it again, once again, in the next class. Most important thing to remember is that it very much uses the fact that all the vertex edges are positive. If all the edges are not positive, then these algorithms are not positive. Okay. Okay, good. So let me stop here. We will see you on Thursday.